Worksheet 18. I was going to do this in class last night, but we got into other things that I felt like were more important and will help you with the worksheets going along. So one of the things I missed was working on this chart. What we've got is 12 volts as a source. We have a source resistance. Everything has some internal resistance. And then we have a load resistance. So what we want to explore here through this chart is when do we get the most load power out? And then what is that load voltage? And what's the source power? Because if something has internal resistance, it will have an internal power drop, so it will get hot or cold, so to speak. Okay? So what I want to do is hopefully I can copy a lot of this to a spreadsheet, and I happen to have one open. That looks familiar. Down here at the bottom, I'm going to add a sheet, and then I'm going to cross my fingers and paste. Look at that. Look at that. So I basically copied that over. Format, column width, we'll do optimal. Sure. So now I can see everything. In order to complete this table, I'm going to add one more column. So I'm going to insert columns before. Whoops, I meant to say insert columns after. We can do it this way. Source voltage. And I gave that to you as 12. It's 12. 12. And yeah, you can copy and paste this down. There are shortcuts in spreadsheets. Okay, so I've got a source resistance, a load resistance. They are actually in series. So my circuit current would be the source voltage of 12 divided by the internal resistance plus the load resistance. So what I'm going to do is I'm going to go in there and I'm going to say equals B2, which refers back to the voltage at this point, divided by, open parentheses, A2 plus C2. Ooh. Okay. A2 plus C2. I see one problem I'm going to have to fix. Okay. Now, it doesn't like the fact that this is 10 ohms and not 10. So let's just go in there and change this. Equals 10. Then I'm going to copy this down. Control C. And Control V. Is paste. Sure. Now this one I got to type these in manually. Equals 1. Do not arrow down. You got to hit the enter key. There we go. Equals 5. Equals 10. Equals 15. And equals 20. Now my formulas will work. So this is the circuit current in the first circuit where I've got 12 volts, 10 ohms of source resistance, 1 ohm of load resistance. Once I get that formula nice, the nice thing about Excel is I can Control C or copy and then highlight these 4 cells and do Control V and paste. So really quickly I came up with the source current. Now my source power is going to be this current squared times my source resistance. So I'm using P equals I squared R. Okay, so I want the power. So that's equal to I squared, which is D2 times D2 times the source resistance, which is A2. And so there's my source power. And I can copy, Control C, and paste, Control V. So when I have a lot of internal resistance and low load resistance, I have a lot of internal power that I have to dissipate. And then as my resistance of the source, which stays constant, gets smaller as compared to the load, I have less power that it will have to dissipate. I'm getting more of it to the load. I'm going to do the same thing to calculate load power. So I'm going to take my current and I'm going to square it. D2 times D2. And yes, you can square things differently if you'd like to. And now I'm going to go to with my load resistance, which is C2. And so you see that this is 10 times this load power. Then I'm going to copy, Control C, paste, which is Control V as in victory. And what you see is that my power starts low, it goes up, but then look at here at the bottom, it's actually going back down. So what this is illustrating is something that people who put car stereos in cars all the time already know, that your resistance of your speakers needs to match the resistance of the internal resistance of your amplifier. So what they will do is called impedance matching. And so when they are the same, say my source resistance is 10 and my load resistance is 10, you see that I get the greatest power out to my load. And that's called impedance matching, and that's why I do this spreadsheet as part of my class, because it really shows quite nicely something that you wouldn't ordinarily think. Now I want to know what the load voltage is. Well, the load voltage is the circuit current times the load resistance. So that is just C2 times D2, and then copy it down, equals C2 2 times D2, enter, and then I Control C, highlight, Control V, enter, and ignore the warning. So that is that table, and it took me, I don't know, 10 minutes here or so to do that, but that is that table. Fairly easy to reconstruct. Don't say that Excel is hard, just do it. You know the formulas for current. It's voltage divided by resistance. You know the formula for power. It's I squared R. I squared R, you know the formula for voltage, IR. So you can easily fill out the table. You can do it manually if you want to. Just takes a little longer. Okay, I got into the other tab of the spreadsheet last night, so I didn't get to these problems. What's the inductive reactance of 1.5 millihenries at 60 and 6,000? I did actually work this one in the class, and I went to back to this spreadsheet. I'm going to go back to my first tab. You know, the spreadsheet in the course does not have a sheet 2. I just added it. So if I go in and say, okay, I got 0.015, and I'm at 60 hertz, I get 0.565 ohms. And if I go to, what was the other one? 6,000 hertz and then 6 megahertz. So I can go back and do 6,000. So I'll just go in and say 6000, enter. You see that my XL is going up, and if I do 6 mega, it says 6 with 6 zeros. 1, 2, 3, 4, 5, 6. You see that my XL is going up as frequency goes up, and I'm just either trying to get you used to working that equation or using the spreadsheet, however you feel like it's best to do it. A circuit containing series components of 0.3 microfarad and 32 millihenries and a resistance at 400 ohms will have what impedance if the applied frequency is 1 kilohertz? Okay, so I know my frequency is 1 kHz. I know my capacitance. I know my capacitive reactance. I know my inductive reactance. So let's go in here and see what I get. So my inductive reactance is 4,000. Was it 4,000 kilohertz? It's terrible when you it's 1 kilohertz, 4,000 ohms. Okay. So it's 1,000. And got to switch back and forth. 32 millihenries, so I want to get rid of the milli, so that'd be 0.032 henries. 0.032, 0.032, enter. And what I've got is 201 for my XL for that problem. So I've got a resistor of 400 ohms. I've got an inductive reactance of 201 ohms. And now I need to do this 0.3 micro. So I'm going to come in here. Now I'm doing capacitive reactance, and I need to know the reactance. The frequency is 1,000. And my capacitive reactance is 0.4 micro. Make sure 0.3 micro. So I'm going to move this 6 zeros. So it will be 6 zeros and a 3. A 0.6 zeros and a 3. And I think I can actually do it this way. I can do it 0.3 E minus 6. So the 0.3 is the number, and E minus 6 is telling me that that it needs to add 6 zeros. So you can in Excel add it in scientific notation. So it's 3e to the minus 7th, so I've got 530 ohms. So now what I've got is I've got 400 ohms, and I can just come down here in a blank cell. 530. Let's call it 531. We'll round. And then my XL was 201. And so I've got 3 devices in my circuit. Uh, 531, 201, 400 ohms. What's the impedance? Everything's in series. Okay, so now I just add up my real and my reactive parts. Well, the only real part I've got is the 400. That's the only resistor in the circuit, so it's 400. 201 is inductive reactance, so it's positive. 531 is negative. So 201 minus 531 is minus 330, right? So I wind up with an impedance of 400 and then minus 300 I. So that would be my impedance. And the value is, you put a parenthesis around both of those and you call it ohms. So that is how you would do this problem, 5-6. Now I'm going to put them in parallel. So now I have to do, now notice the same values. So the fact that we calculated the 531 and the 201, we don't have to recalculate because I'm using the same frequencies. So you would just then use these numbers and put them in parallel. Well, if you put them in parallel, you do 1 over the impedance. So you would solve 1 divided by 400 and 1 divided by the 201 is positive I. So 201 I, and then 1 divided by minus 531I. Because remember, capacitive reactance is always in the minus I direction. Inductive reactance is always in the positive I direction. I don't have Scilab open, but we can open it. So, come on, Scilab. You can do it. You can do it. Now I'm starting to wonder. Did I double click it? Or did I single click it? If you get impatient, you double click it, and then you got it open twice. Okay, so we're going to do 1 divided by 400 plus, and this is how you do it in Scilab, 1 divided by, now I've got to do the parentheses, because if you don't do parentheses, Scilab is just as dumb as a calculator. It won't put everything, combine everything in the denominator before it does the 1 over part. So it's 201, and then to enter I in Scilab, you got to do shift 8, which is the multiply sign, and then Scilab has a constant. So if you do percent I, it understands that you are doing the square root of -1 there. Okay, so similar thing, 1 divided by minus 531 times percent is shift 5 on a keyboard, I close parentheses. This will do your common denominators for you, and this is what you get. Now remember that this answer is 1 over the answer we're looking for. So what I have to do is I have to invert this, because up here all this is equal to 1 over z. So when it calculates this, it's still equal to 1 over z. Well, I want it to be just be z. So to finish the problem, I just do 1 divided by answer. Now see that it labeled this as answer, so when you 1 over the answer, it's taking this value and it's putting it 1 over that value, and there's my answer. So this would be the impedance of those 3 devices in parallel. It's 158 plus 190, 196I. And I think this is probably a good place to stop this video. Okay. Yeah, this is a good place to stop the video. So I got through 7 and 8. Let's go back to Scilab so y'all can see that. So when you get to the parallel, don't panic. Yes, you can work this out by hand, absolutely. You still got to find the common denominator, and you got to either make them all I's or not. Or you can just use a calculator will do it if you enter it right. Yeah, I even think the TI-83 will, and 84. The TI-84 does have problems when you're solving matrices with imaginary numbers, and ultimately that's where we're heading. So you need a TI-85 or above if you're going to use a calculator, or something with those, something with the capability of a TI-85 or above. It's hard to find a TI-85 anymore, so you can probably find a TI-89. So anyway, that's how you would come up with it. Parallel formula is just like the resistance in parallel. I'm using impedances in parallel. Same formula, same thought. The only difference now in the AC part is you have these imaginaries, and let the software do the number crunching for you. Okay? Anyway, I thank you for watching.